So in this video, I'm going to take you through 5.17.1, which is going to go through coupled differential equations. And notice that it's sort of like a system of equations, but for the first one, we've got dx dt. The second one, we have dy dt. And so we've got, these are functions of t with respect to time, but we have two variables that are affecting time. And so if you went through the big picture, they go through some sort of real life situations where two variables might be affecting each other. Like one good example is competing businesses, how an increase in sales in one might cause the other one to decrease, or maybe an increase in sales in one business is actually causing an increase in another. So these are situations where this could happen. And now to solve these, we've got this formula right here, which A and B are constants, and we need to have an initial condition to figure out what A and B are. And then this e to the lambda 1t, lambda 1 is our first eigenvalue, and then e to the lambda 2t is another eigenvalue. Okay, and then we've P1 and P2 with those arrows on the top, those are vectors. So they're going to look like this, x, y, vertically. So we spent time on this in chapter 1. I think it was 1.14. So you might want to go back and review how to find eigenvalues and eigenvectors, because this is a good way where they're going to come up on the exam. And so I wanted to go through the first example with you because Cognigy leaves out some things and it's kind of hard to figure out. So dx dt equals 3x, dy dt equals negative x plus 2y. So that's our system of diff EQs, and this is our initial condition, and then they tell us to evaluate and plug in when t equals 1. So the first thing we have to do, like here are the steps from Cognigy, is rewrite the system as a matrix. So this first dx dt is only in terms of x. You could think of this as being like plus 0y. That's why there's a 0 here. And this negative 3 goes here. So we're just pulling off the coefficients. 2 is there, and negative x corresponds to the negative 1. So rewrite it as a matrix, and you don't even really need this part. So then to find the eigenvalues, we just look at this first diagonal, and we subtract lambda from each one. Okay, and then what's missing here is actually you're supposed to subtract the product of the other diagonal. So 0 times negative 1 is 0. So that's why they leave it out, but they don't really even tell you. That's going to come up on the other examples. The determinant is always, if we go back and we call this A, B, C, and D. So you're only going to have to do this for a 2x2 matrix. Then the determinant is A, D minus B, C, and you set that equal to 0. Okay, and actually it's A minus lambda times D minus lambda minus BC. So that's the actual formula for the determinant. This case is a little bit simplified because the diagonal product here is 0. So then when we keep going, to figure out lambda, it's easy. You just plug in, 2 minus lambda equals 0. If 2 minus lambda equals 0, then lambda has to be 2. And it doesn't matter which one is which. Right here they say lambda 1 is negative 3, lambda 2 is 2, but you can switch them, it doesn't matter. So then the other one's going to be negative 3, because negative 3 minus negative 3, that's going to turn into a plus, that's also 0. Okay, so then the next step, is to figure out the eigenvectors. So here they're just showing you there's two ways to do each one. So if we start with -3, lambda 1 is -3, then this part is this part, -3x, -3x. Notice here, -x plus y, -x plus 2y. I mean, the left side is just whatever your diff EQ says, but the right side, they're just putting the lambda value on the front of x and y. They're doing the same thing over here. Notice these don't change because that's from our diff EQ, but then they just put the lambda value in front of x and y. Okay, and then you solve those, and you want to get x on one side and y on the other side. In this one, y cancels out. But either way, like if we try to solve this one, it's really nothing's going to change. It's just saying -3x equals -3x. So we don't worry about that. But this one, -x plus 2y, if you solve plus 2y, if you solve this to get y on one side and x on the other, it doesn't matter which side is which. But if we just subtract 2y on both sides, you can see we have -x over here, and here we have -5y. Multiply both sides by -1, x equals 5y. Okay, and now we want to try to rewrite this as a simplified vector. So if you just make a table and you say, okay, well, when y is 1, plug in 1 for y, and you get 5 for x. And so then they just rewrite it in vector form, x on top, y on the bottom. You could rewrite this, in another way. What if y was 2? Then x would be 10. Or if y was 3, x would be 15. Any of these vectors would work, but we want to try to rewrite it in the simplest form without any fractions. So that's why they went with 5 and 1. And the second one, again, we don't solve this equation, we solve this one down here. And so when you subtract, if you subtract 2y on both sides, the y just cancels out completely. So you get -x equals 0, which means x is 0. Okay. And so if x is 0, then that's always going to correspond to this just unit, this basic vector, 0, 1. X is 0, y is 1. So then the next step is to apply the eigenvalues and eigenvectors into the formula. So again, the formula is given in your formula booklet. It's a to the e minus lambda 1 t times the first eigen vector, so they called that P1, and then plus b to the e minus lambda 2 t, and then times vector 2. And it doesn't matter if you switch these around, as long as you keep the eigenvalue and the eigenvectors together. So that's why they're plugging in 3 and 2 here, and then the eigenvectors that we just had. And now to solve this, all you have to do is you sort of ignore this part and multiply a times 5 plus b times 0. So a times 5 plus b times 0, and set it equal to the first initial condition. And then the second one, you do a times 1 plus b times 1 and set it equal to 2. So a times 1 plus b times 1 equals 2. And now you want to solve these for a and b, and that's what they have here. A is 1/5, b is 9/5. And then you plug those values in for a and b. That's what they've done here. Okay, that's the next step. And then to solve, you just take, so like ignore the y value for now. Just do 1/5 e to the minus 3 times 5. So 1/5 e to the minus 3 times 5, I can put the 5 here, and that's going to cancel out. So that's why they just have e to the minus 3. And then you just evaluate with the calculator. The next one is now we have to do the y coordinate and ignore the x coordinate. So 1/5 e to the minus 3 times 1 is just that, and 9/5 e to the 2 times 1, and then evaluate with the calculator. Okay, and that's our solution when t equals 1. So I know it's a lot of work, it's very tedious, maybe not that gratifying at the end. So the rest of this example that they go through, like they're just, for part B, you shouldn't have to do this. They're using Euler's method and going through, 500 iterations. There's no way you're going to do that. But they're just showing, they're comparing the Euler's approximation here to what we got using the formula. And it's very close. They just want you to know that the formula is called analytical results, and then Euler's method is the approximation. They just want you to see how close it is. So that's it for example 1.